This video is a review on energy, heat, and work. So it's from lecture 29, if that helps you keep track of it at all. But to start off, we want to talk about the first law of thermodynamics. And that is that energy can neither be created nor destroyed. It's just passed and changed the form, but you can't create and you can't destroy energy. It's just passed around from system to system. And so that means that the delta or change in the energy of the universe is always going to be equal to zero, which means that the energy of any system plus its surroundings is going to equal zero. So that'll come into play with some of the problems. And for energy, we move this so you can see that. Energy also equals Q or heat plus work or W. And there are three kinds of energy we talk about. The first is radiant or light, and the second is potential, and third is kinetic. So here we have a little girl on a swing, and because she is moving, she has kinetic energy. So kinetic energy is energy of motion, which is different from potential energy, which is the energy system or an object has due to their position. So because this car is at a high altitude on a hill, it has the potential to do something. In this case, go down the hill really quickly and convert that potential energy into kinetic energy. But while it's up here, it has all this potential energy. And as it goes down, it loses potential energy and gains kinetic energy. So there are multiple forms that things can gain energy and ways we transfer energy, but almost everything we do is a result of work or some sort of heat transfer. So potential energy, if we want to look at it on an atomic level, if you kind of remember from when we talked about bond lengths, the atoms want to be in the most stable position and length from each other. So at their most stable position, right here, they have their lowest potential energy, which means that they don't have a lot of potential to like move because they're in a stable position. So there's going to need to be some sort of heat transfer or energy transfer to cause those atoms to move and break from each other. Or even to come closer. As you can see, if their bond length goes, if they come closer together and their bond length decreases, then there's potential energy because they're too close, so they want to break away from each other, and that want to break away from each other, that is electrostatic repulsion, and that's potential energy. But then as they move further away from each other, they come at a stable level, and um, there's no real attraction to move. So there's no potential energy, or close to none. And then as they come further and further away, they're going to want to come back, right? Like a magnet. If you pull it apart, it comes back together because of electrostatic attraction. Same thing there. The more you pull it apart, the greater its potential energy up until or up until a point, right? So as you're pulling them apart, the potential to snap back is going to decrease and decrease and decrease until eventually they don't really have any potential energy or electrostatic attraction to each other. Kinetic energy is the energy of motion. So whenever something is moving, it has kinetic energy. And that can be described in three ways. Translational. So here we have a molecule of N2. It can move along any of the three axes. And that's translational when it's like moving or sliding. We have rotational, which you can kind of pretty easily imagine, just when it's moving. So this can happen when atoms are in a liquid phase. They can rotate around, not so much in a solid phase. But in a gas phase, they have a lot of translational kinetic energy because they're moving around a lot. And same with a liquid, but it's a lot more in a gas than it is in a liquid. And the third form of kinetic energy is vibrational energy, which is when the molecules are like vibrating with the bonds and they're vibrating around. And so when they're doing that, obviously they're moving a little. So it's not quite translational where it's all going together, but they're just moving within those bonds and around that attraction. And so here, now we want to talk about internal energy. And the internal energy is is what a system or an object has, and it is equal to the kinetic energy plus the potential energy. So any system or object will have the internal energy, its own internal energy, which is the sum of the kinetic energy and the potential energy. And so part of an object's internal energy is affected by what kind of system it is. So here you can see that we have an open system, and that is where heat is transferred out or in, and matter can shift around, and matter can be put into the system or taken out. And that I'll have some pictures here after, but that's like a boiling pot of water. Like the water can escape from the system, so all of that matter is escaping from the system. Or you have a closed system where the matter is not leaving, just the heat. So that's kind of like if you put a pot of water to boil and you have a lid on it, only heat is going to escape. And obviously, if you have like steam coming up, that is going to be some water matter, but mainly in closed systems, it's just heat that's escaping. And then you have an isolated system, and this is like a perfect thermos where no matter gets in or out and no heat gets in or out. So um, it's totally isolated. And when you talk about systems, you want to keep in mind the surroundings because, like we said, with energy, the heat, the change in heat of the system will usually will equal the change in heat in the surroundings because it has to equal zero because it's not going to create or destroy it. So when the system, where's my mouse, gains energy, the surroundings lose energy. When the surroundings gain energy, the system loses energy. So here are some pictures. We have a pot of water boiling without a lid. So this means that heat is being transferred out of the pot, and it's an open system as you can put food to boil in there too, in the boiling water to heat up. Um, and then we have a closed system where, see, it's trapping the steam, and but the heat can't escape. And so you can't put anything in that, obviously, without taking the lid off, which releases all the steam. And these are the main two types of systems that we work with a lot. Another example of a closed system is an ice pack. So if you have one of those ice packs where you like kind of bend it back and forth to make it cold or heat up, depending on the pack you have, it's a closed system because it's all in a bag, a sealed bag. So it's not going to lose any matter and it's not going to gain any matter because all of that chemical is in a sealed bag. All right, we also want to talk about state functions and what those are. And I really liked how Dr. Mortensen used a state to remember in his example, so that's what I did too. But here we have Virginia, and if we think of it as this is our initial point, and this is our final, so initial is on the left and final is on the right, on the bottom of the state, we can get from point A to point B going straight across, or we can go along the northern edge of the state, along the jagged top. And either way, we're going to get to point B from point A. And state functions when you're working with state functions, it doesn't matter the in between. As long as you get from your final from your initial to your final, it doesn't matter. And so the state functions that we work with are these, and there's an acronym to help: PVT hugs. So pressure, volume, temperature, enthalpy by represented by H, internal energy represented by U, Gibbs free energy represented by G, and entropy represented by S. All of these are state functions and you'll see on the like equation sheet a lot that they have delta or the triangle next to them because we're just looking at final minus initial. So our non-state functions are our heat and work. And you know that work from any physics class, you'll know that work is force exerted over a distance. We're also going to look at it as pressure exerted with a volume. And so back to the systems and surroundings relationship, when heat flow is from the system to its surroundings, or when the surroundings are hotter, getting hotter, it's negative because the system is losing energy. Our Q is going to be a negative value. Or when you have a gas in the container, like a balloon, and it's expanding, it is doing work on the surroundings, which means the work will be negative. But if the system or the surroundings are compressing the gas, the balloon, that's going to be a positive work value. So these, we do keep track of like the flow and not necessarily the final minus the initial. These we don't work with that. So in talking about heat and energy, we want to know which are endothermic reactions and exothermic reactions, because whenever you have a reaction, there's some sort of change or transfer in our heat and in our energy. So exothermic reactions are, and exothermic phase changes that we deal with a lot are condensation, freezing, and deposition. Excuse me. When a gas condenses to a liquid, it is losing energy, like the molecules in the gas are losing energy into the surroundings. So the surroundings will be hotter because they're gaining that energy. I'm going to put this back up here. Hopefully the cameras. Hopefully that's working for you. The molecules are losing that energy to the surroundings, making the surroundings hotter, making it an exothermic reaction. Same with the liquid. Liquid molecules, to become, when they're freezing, they lose energy, kinetic energy, and they become solid and release energy into the surroundings, which is an exothermic reaction. And same with deposition, obviously, if you're going from gas to a solid. And so we have the flip of that, which is an endothermic. And if you go from a solid to a liquid, the molecules in the solid are gaining energy. And so as they gain energy, they break the bonds they have and can move more freely, which is a liquid. And then even more of that is liquid going to a gas, where the molecules gain even more energy, more kinetic energy to break their bonds and become gas and can move around more freely. But as they gain energy, the system is losing energy. So if we go back to this, if we have ice and it's our system and it's gaining energy, the surroundings are losing energy. And when ice gains energy, it becomes a liquid, or when a liquid gains energy, it becomes a gas. But when the surroundings are gaining energy, that means our system is losing energy, which means the gas is becoming a liquid, which then becomes a solid. All right, so back to phase changes. So, and you can see that usually as the temperature increases, the kinetic energy is going to increase, which makes our endothermic reactions more probable, and which also means that our kinetic energy is relative to our temperature. And you can also see that the energy input is on the same kind of graph, or the same like it works in the same way as temperature does on phase changes. So as you're inputting energy into a system or into a substance, it's going to go from solid to liquid to gas because you're inputting energy into it. And I like to look at it at a molecular level. So if we go from a solid, we can see that the molecules don't have like any kinetic energy. So as you put in energy into the molecule, they move around more freely, which is a liquid. And if you put in more energy, they become a gas. When you put in energy, you take out energy from the surroundings, which is endothermic. When the surroundings are losing energy, it's endothermic. And when the surroundings are losing energy, the substance is gaining energy. And the opposite of that is true. These gas molecules, a lot of kinetic energy, and when they lose energy, they become liquid. And when they lose even more energy, they become solid. So when the substance loses energy, the surroundings gain energy. And when they do that, they're heating up, which means an exothermic reaction. So here are some examples. When water and acid react, it releases energy. When a campfire is burning, it releases energy. When the freezing water is turned into ice, it's releasing energy. And so an endothermic, the surroundings here are losing energy because they're putting it into the ice. So even though the ice is getting warmer, the surroundings are getting colder. And that's what makes it endothermic. And sometimes hard to remember, but if the molecules are speeding up more, it's because the surroundings are getting colder, which is endothermic. And so here are some practice examples. You decide if it's an endothermic or exothermic. I guess I can pause. So here are the answers. So answer A, water evaporates off a shower door. So the shower door is going to be colder than it was before because the water molecules are gaining that energy and heat to change into gas and water vapor. The acid tablet being added to a pool and the surrounding water heats up. Whenever the surroundings are heating up, that tells you that's an exothermic reaction, like a fire. I guess we're going to get to that. Ammonium chloride is dissolved in water and the solution cools, so the surroundings are cooling. Really good indication that's an endothermic reaction. And of course, we have a log burning in a campfire, which is exothermic because it's releasing heat. We measure energy and heat in these units, and heat more in joules and energy in all of these. Joules is just the standard unit, or standard unit of energy. Calorie is the heat needed to raise 1 gram of water by 1 degree Celsius, and 1 calorie equals 4.184 joules. Calories with the capital C that you'll see on the food, the nutrition information, it's 1,000 calories. We also work with liters times atmosphere, standard atmosphere units, and that's when we're working with work and pressure times volume. And 1 liter times atmosphere is equal to 101.32 joules. So we have joules or diamonds and then calories. So work. From physics class, you'll know that work equals force times distance. But with problems here, we're going to use work as a function of pressure times volume. So whenever you're dealing with that, if it's like STP, standard temperature and pressure, pressure is always going to be 1 atmospheric unit. And same with the most problems will probably be in 1 atmosphere. But the question is, why is there a negative here? So here it's a little backwards thinking. But if your system or the surroundings, like this container with this lever thing, are compressing the gas, it's doing work on the gas, which is positive. So our delta volume, delta V, is going to be negative because it's compressing. Our final is going to be smaller than our initial. And so if this is negative, we put this negative out here to kind of cancel that out and make sure the work is clearly positive. And the vice versa of that. And the opposite of that is true. When the system is expanding, the gas would be expanding, then it's doing work on the surroundings, and that equates to a negative work. And here we can see the definition: pressure is defined as the force divided by the area it's being exerted on. So we also want to talk about enthalpy. Enthalpy is a little different from internal energy. And again, internal energy is the kinetic energy plus the potential energy. Enthalpy is a measure of the internal energy plus the energy expended to push aside surroundings to make space for the system, product of pressure and volume. So it has to do with work as well. Our enthalpy equals our energy and or plus our work. So we also want to know that when pressure is constant, our enthalpy equals our heat change. And then in other lectures and other review videos, you can remember what exactly these two are, but we have an enthalpy of fusion, or the energy change that occurs when a substance is being fused or like freezing. And then we also have the enthalpy of vaporization, which is the energy change that occurs when a substance is evaporating, vaporizing. And when that happens at a constant pressure, these are both constitute as heat transfers. So again, enthalpy versus internal energy. Enthalpy, they're both thermodynamic terms, but the main difference is that enthalpy is the heat absorbed or evolved during chemical reactions that occur in a system, whereas internal energy is just the sum of potential and kinetic energy in a system. And from Dr. Mortensen's slides, the internal energy of a system is an intrinsic value of the sum of the potential and kinetic energy possessed by a system. Enthalpy defines the energy of a system, considering its internal energy as well as any additional energy required to displace its environment. So this part, as well as any additional energy required, comes into play with the extra PV. So it's not just the internal energy, but it's the energy needed to do this. So here's a practice problem. An internal chamber expands due to a combustion inside of it. So you want to think volume. If the chamber expanded from 5 liters to 6.5 liters after absorbing 10 joules of energy from the combustion, what are heat, work, and energy for the gas molecules inside the chamber? And assume the pressure stayed equal at 1.3 atmosphere, standard atmosphere units. So you can pause and kind of work it out. It's really similar to the problem that Dr. Mortensen gave us in the lecture. Hopefully a little more practice can help you own the skill. So our heat is going to be positive because it's absorbing energy. The system is gaining energy, or heat, excuse me. The work, so PV, so our pressure is 1.3, and it stays constant, so it's fine. And our chamber is expanding, so 6.5 minus 5 liters, which gives us, so that equation gives us negative 1.95. And again, because it's expanding, it's doing work on the surroundings, which means it's negative. So negative 198 joules, because we multiplied this by 101. And so our delta E is just W plus Q. So that's 10 joules plus 190, negative 198 joules, and that's negative 188 joules for our energy change. And so the most important thing that you want to remember is that during this lecture, Dr. Martin said, you never put calorie at the beginning of a sentence, otherwise you're just a maniac. I don't recognize teal as a color. And enthalpy is a really fun thing because it's not really a thing at all. Just a little humor for you there.